I think this is going to be a kind of tricky concept to explain in a video, but I'm going to give it a go and we'll see how the video turns out. We're going to look at the universal gravitation equation here, and this means the force of gravity acting on something in a more general sense. So it doesn't have to be on the Earth, it could be anywhere, and so it's really the gravitational interaction between two objects. And that equation is given by m1, m2, times the universal gravitational constant. The universal gravitational constant you should think of as a constant that just makes the units work because all these other units were invented before this equation came along. Times, we use the letter r to represent radius, but this is the distance between the two objects squared. So if I have object 1 here, m1, and I have object 2 here, m2, then the distance between their centers is r, and g, again, is just a constant to make the units work, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Now you can obviously see that this universal gravitational constant is designed to be used with the metric system. If you were using sort of standard units that were not metric like the imperial system, it'd have a different value. So I think the fact that the force of gravity is proportional to the mass of the objects involved is somewhat clear, because this force, we say, exists because we're dealing with the gravitational interaction or attraction between these two objects. But why is it an inverse square relationship? Why, as you go further away from the object, does the force vary as radius squared? The idea here is, imagine that this object, m1, is generating the force of gravity on m2. So here's m1, and he's generating force of gravity on m2. Imagine that m2 exists on a giant sphere, and that m1 is attempting to exert this force of gravity in all directions. I'm drawing it in 2 dimensions, but remember, this is really a 3-dimensional issue. Then if we imagine the amount of m1's ability to exert the force of gravity spreading out, it's spreading out on a surface area of a sphere, where m2 is only one location on that sphere of a fixed area. So if m2 was here, the sphere that it would be spreading out on is this big, whereas if, let's say, m2 was right here, it was a little closer, it'd be spreading out over a smaller sphere. So let's say that this force of gravity has a specific amount of possible force that it could generate, and I'll just call that x. Then in this situation, that would be spreading out over a sphere with surface area 1, so it would be spreading out over 4 pi r1 squared. That's the surface area of the sphere. Now we're assuming that this 4 pi is a constant and that x is a constant, so I can lump all those together and I can call that some other constant, y, over r1 squared. Now let's imagine that this object was further away at r2. Now, so that's in case 1, our constant amount of possible force is being spread out over a larger sphere. And so because r1 is bigger than, or r2 is bigger than r1, this denominator is getting bigger, and so the amount of force that actually hits the individual location has decreased. Again, for the sake of argument, we can say that those constants can all lump together to make one constant, make it a little simpler. But what we can see is that as the radius changes, the force of gravity changes. And the force of gravity, because it's spreading out over that surface area, that sphere, means it's spreading out over a larger surface area, and the surface area is growing as r squared. So since the surface area is proportional to r squared, so as the circle gets bigger, I shouldn't say circle, I should say sphere, gets bigger, the force of gravity has to spread out over a larger area, this means there is less force of gravity for any specific spot on the sphere. I guess this would make more sense if we were thinking about, say, how many particles from M1 we're going to hit M2. So if we imagine the particles are all spreading out in different directions, at this location, because the surface area is smaller, more of the particles would hit M2. When I go further out, and I have the same sized window, but I'm further away, less of the particles are going to hit M2. How many less? Well, it's proportional to the surface area, right? They're being divided over the surface area. So if the surface area is going up by r squared, the amount of particles that are hitting that other object are going down by 1 over r squared. So that's how we get our universal gravitational equation, and this is the gravitational equation that we have to use when we have two general objects which are exerting a force of gravity on each other, in space or something like that. I'm going to talk about how we simplify this equation to deal with the force of gravity on Earth and what the resulting acceleration due to gravity is in the next video.